Hello, welcome to this clip going through a question from the OCR 2013 F321 paper. I've chosen this question because it covers lots of different topics from the first year of the A-level course, and therefore is a really good synoptic question to use if you're starting to prepare for exams where those topics are likely to appear. So end-of-year exams or final A-levels would be good examples of such papers. So in the first question, it tells you about a reaction between phosphorus and sodium hydroxide that you might not have come across before. And the first part of the question asks you to use oxidation numbers to explain why this is a disproportionation reaction. So remembering what disproportionation is, we can start doing this by applying oxidation number rules. So I'm starting out by putting the oxidation numbers over everything that I can apply them to. So sodium, oxygen, hydrogen, they're covered in the oxidation number rules. So I need to think about phosphorus now. So you can see that phosphorus has two changes. It goes from 0 to -3, which is a reduction, and it also goes from 0 to +1, which is an oxidation. So you need to say in which species it is 0, and which species it ends up as +1, and the fact that's an oxidation, and do the same for the reduction process as well, but using the oxidation numbers as you go. So we can go down to the next part. So to do this, I'm going to take a little bit of the previous part of the page and just stick it there so we can use the equation to do the volume of phosphine gas. So this is now moving on to moles and gases. So looking at the question as well, you can see that it tells you to calculate the volume of phosphine gas in centimetres cubed at room temperature and pressure. So that means V equals 24N. But I've just realised I haven't put in a highlight on centimetres cubed. So I've quickly altered my V equals 24N into V in centimetres cubed, meaning 24,000 N. So we can apply the data moles equation moles answer technique to this because it's like all mole calculations, the DMEMA technique will work. So using the data that we actually have, we can work out that we have 0.015 moles of P4, and because you've got a 1-to-1 mole ratio, you can simply use that and multiply it by 24,000 because it's going to be the same number of moles for pH3 as a gas. So this is what we're given in the question, the final part, writing the equation. We have P4O10, so therefore that must mean you need 4 pH3s. If you do that, you now have 12 hydrogens, so you need 6 H2Os, which means you have 16 oxygens on the right-hand side, so you need 8 O2s on the left, like that. So now we can go to the next slide, which is the next part of the question. So this starts by talking about why is Na3PO4 described as a salt of H3PO4. So this requires you to think about what the word salt means at A-level. Please don't try and default to GCSE type thinking here and just say, oh, it's produced when an acid and a base react. You need to go a bit further than that. So you need to say that the hydrogen in H3PO4 has been replaced by Na+. So you really need to put in, I suppose, that the H+, hydrogen ions in H3PO4, has been replaced by Na+, which is a positive metal ion. So the next part is another application question. We can again use data moles equation moles answer. So following the data moles equation moles answer technique, you find you actually get the answer quicker this time because it just is a more simple calculation. There's no harm to do DMEMA because it'll actually serve you for any mole calculation you actually want. So let's move the page down now a little bit. So what they want you to do is to look at this one here, the equation for the preparation of Na3PO4 from NaOH and H3PO4 is shown below. Calculate the volume of 0.200 moles per decimeter cubed of NaOH that reacts exactly with 15 centimeters cubed of 0.100 moles per decimeter to the minus 3. Now, we've already worked out what 15 centimeters cubed of 0.100 moles per decimeter to the minus 3 H3PO4 represents. So you don't have to do that again, you just have to go with the equation bit. So you can simply multiply the number of moles of H3PO4 by 3 to get 4.5 times 10 to the minus 3 moles. Time to get your answer. So that gives us 22.5 centimeters cubed, not forgetting, of course, to divide the concentration by 1,000, as the volume required is in centimeters cubed, not decimeters cubed. So we can now go on to the next slide, next page rather. So here we're switching from calculations onto recall of intermolecular forces. Now remember that different boiling points will help us think about which intermolecular forces might be present. So ammonia has a much higher boiling point than phosphine, and obviously what you're looking at is both of them are hydrides, so that it's possible that if it's bonded between hydrogen and nitrogen, oxygen and fluorine, you could be looking at hydrogen bonds. So in NH3, hydrogen is bonded to nitrogen, there's a lone pair on the nitrogen, so you get hydrogen bonding. But in phosphorus, this doesn't happen because phosphorus isn't nitrogen, oxygen, or fluorine. So this drops down to permanent dipole-dipole interactions. And then it says suggest why pH3 has a lower boiling point than NH3. So where it says suggest, that means that you don't need to actually know this, but just take an educated guess using knowledge you already have. So because the question is comparative, in other words, it mentions a lower boiling point than, you need to mention both of the things that are mentioned in the question in your answer. So the permanent dipole-dipole interactions in pH3 are weaker or require less energy to overcome than hydrogen bonds present in NH3. So we can now move the page down a bit. So it says at this point that NH3 reacts with molecules of BF3 to form H3NBF3, shown below. So this is a new molecule perhaps that you might not have come across. So in this case you've got to recall what is a data covalent bond. So it means that both electrons in the bond pair have been provided by the same atom. So in this question what I've done is I've highlighted the instructions. So I know exactly what to do. So I'm going to take the displayed formula of H3NBF3 from the previous page and pop it on this one so that we can use it to work out how to do our dot cross diagram. So there it is, and if we think about the number of electrons in boron and the number of electrons in nitrogen, nitrogen has 5 electrons, 2 more than boron, so the data covalent bond will be, the direction of donation will be from nitrogen to boron. So I've just realised I got the N and the B the wrong way around in my data covalent bond, so I can pop that in there. So if I populate my data covalent bond first, using my nitrogen atom having 5 electrons, I can see that I've got dots for my hydrogens and crosses for my nitrogen in red. So now if I look at my boron, I know it only has 3 electrons, so I can put its electrons in as circles, and the fluorine electrons in each bond between B and F in as blue crosses. So remembering that it asks me to show my outer electrons only, I need to put in the outer electrons for the fluorine as well. So being halogens, they'd have 7 electrons of their own, so I need 6 more electrons, ideally paired like that. So we can now move the page down a little bit and see that the next part is asking me about bond angles. So the FBF bond angle in BF3 is different from the FBF bond angle in H3N BF3. So the starting point with this is to look at the table, and you can see that one of them, the BF3 molecule, is one that you'll have seen in textbooks already. It's quite commonly used to illustrate trigonal planar or 120-degree bond angles. So that would be an example of recall. So I can put 120 degrees in for that. But H3N BF3 is more of an application because we don't know what the shape of the nitrogen atom is around H3N BF3. We have to try and deduce that. Now if we take NH3 and highlight the bit of the next question where it says the HNH bond angle in NH3 is 107 degrees and stick a little lone pair in on top of the N, you might notice or think about the nitrogen in H3N BF3 as that lone pair now becomes a data-covalent bond. It becomes a bond pair. So now this means that the shape around the nitrogen atom in H3N BF3 is tetrahedral, and therefore that would mean that it's actually 109.5 degrees. So the final part asks us to explain why the student might expect the HNH bond angle to be larger in H3N BF3 than in NH3. So we use valence shell electron pair repulsion, or VSEPR as it's sometimes called, and we state that the nitrogen in NH3 has 3 bond pairs of electrons and 1 lone pair, but in H3N BF3 the nitrogen now has 4 bond pairs and no lone pairs. So what's happened is that the lone pair has now become a bond pair, and because lone pair repulsion is greater than bond pair repulsion, we can draw the conclusion that less repulsion will mean a larger bond angle. Okay, so that takes us to the end of this clip. Hopefully it's been a useful look at not only a challenging question, but how you need to have fluidity going from one topic to another as you do a synoptic style question. So until next time, thanks for listening and see you soon.